Okay, this week we discuss about the imperfections in solids. It's an easy topic compared to the ones that we have done. So the things are getting easier, okay? Only one topic which phase diagrams, that after that you will have like, easy topics. But the previous knowledge is needed for those topics. So in the imperfections, let's see what we have here. So we will discuss about what types of defects arise in solids. So when we consider solids, we will be discussing about ceramics and metals, what kind of defects that we have. Can the number and the type of defects be varied and controlled? How do defects affect material properties? So these are, when you know about the different types of defects, you will be able to think about these stuff, okay? So you can do more research and find more information about those. Okay, so let's see what we are going to study. So there are different types of imperfections. Imperfection is it's a defect. However, sometimes we are using those defects. So point defects, we can divide these defects into 4 categories: point defects, line defects, surface defects, and volume defects. So under the point defects, we can have vacancies. Vacancy means you have a missing atom. So in the repeating cells, in the repeating lattice, you will see a vacancy. Interstitial, substitutional. So I'll show you this with pictures. Shoki effect, Frankel effect. So these are the point defects. It's related to a point. Line defects can be, it's a defect along a line. So it is two-dimensional. So edge dislocations, screw dislocations are the line defects. We can have surface defects, which you have like, one surface. So here we can't say two dimension, we can say just 1D, it's along a line, okay? But surface may be two-dimensional, so grain boundary defects and twin boundary defects are the surface defects. We are not discussing about the volume defects, however, volume defects also can be, volume defects are 3-dimensional, so this will be 2-dimensional, this is 1-dimensional, this is just a point. So volume defects we are not going to discuss, however, in solids, we can have voids, cracks, inclusions, precipitates, we can have them, but like, we are not going to discuss them. You can understand it when we discuss these ones. Okay, let's start with the point defects in metals. So metals can have vacancies. So we can see a missing atom, missing vacant atomic space. So this is a vacancy. So metals, metals have just one element, so it can be a magnesium. So all the atoms will be magnesium atoms, or else we can have zinc. So zinc, all the atoms will be zinc atoms. So that's why we have the same atoms, same colored spheres here. So this we call a vacancy defect. And we can have a self-interstitial defect. That means you have an extra atom in some position. So you can see here, we should not have this one. This one, we should not have it. But we have an additional atom in a place where it should not be there. That kind of a defect we call a self-interstitial defect. So anyway, in metals, like, when we have a different element here, we will discuss it later. For the time being, we can say there is a additional magnesium atom in the magnesium solid here. So that will be a self-interstitial defect. So it make the planes dislocation. See, it's shifting, it's pushing away. But here it is pushing towards the vacancy. So you see, it's make a distortion of planes. Both the cases, vacancy or else self-interstitial defect. We should be able to know how to find the number of defects. So we have an equation for that. So the number of defects, we use this NV, and that gives us the number of defects. It's equals to N times E to the power 1 minus QV over KT. So here, this N means the number of here the number of potential defect sites, number of sites, and E, you know, the exponent you have is in the calculator. So Q means the activation energy, minimum energy to create one vacancy. So that we should supply energy to create a vacancy. So otherwise it is stable and it's nicely staying with the repeating unit in a periodic way. T is the temperature, absolute temperature. That means the temperature in kelvins. And this constant here we call the Boltzmann constant, and it's a known value. So we can find out the number of defects using this equation for metals. When we discuss about the ceramic, the equation will be slightly different, but for the metals, equation will be this. So we normally use NV over N. N means the number of sites. So the defects, percentage of defects per site, we can express it as a per site. So in your lecture notes, it has in this way. So this is the same thing. The only thing is this part is exponent to the power. Okay. So if you see here, it is easier for you to understand. So this part, this will be exponent to the power. So here, don't get it like, you know, this should be to the power of this. And N is again the number of defects. NV is the number of defects. N is the total number of atomic sites. Q is the activation energy, as I have mentioned. K constant is the Boltzmann constant, and T is the absolute temperature, which is the temperature in kelvins. So we have these questions in the tutorial. We will be using this equation and finding the answers. Any questions so far? So it's an easy topic. I hope you understand. I'll move to the next one. Okay, now let's see the defects in the ceramic. So ceramic is what? Ceramic has two components, isn't it? Mostly like a cation and an anion. So ceramics, they have ionic bonds. So they give electrons, and some element is accepting electrons. So they have cations and anions. So cations means what? Anions means the negative ions. Cations is the positive ions. So I told you, if you consider sodium chloride, sodium would like to give one electron to the chlorine and be stable. So outermost shell will be fully filled. Chlorine would like to take an electron and make the outermost shell fully filled. I told you this one many times. So cations are smaller. Why is that? They have more attraction towards, they have removed one electron. They have removed electron from them. So they are smaller. And anions are taken electrons. So their attraction towards the nucleus is less. So nucleus, you have positives and you have electrons around it. So when you have more electrons, the attractions will be like, you know, less. And we have additional electrons here. So you can identify which one is what just by looking at the size of these ones, ions. So these big ones are the anions, and the blue ones are the cations because they are small. So you can have vacancies again in the ceramic. So vacancies normally happens only with the cation. So cations missing. So small ions missing. So you can see a vacancy here where you have small ions missing. And also you can have the vacancies in the anion where you can see the big ions are missing. So cation vacancies and anion vacancies can be there in ceramics. And also we can have interstitials. So interstitials exist in cations where you have a shift. So you have an additional cation here. See? So that is a cation interstitial. So we don't have anion interstitials because anions are big and they don't stay like interstitial. They can't squeeze in and have go into this structure. So this is this one is a cation interstitial. So interstitials are not normally observed for anions because anions are large relative to the interstitial sites. So interstitial sites are these sites here. Are we good? Any question? So this is, as I have mentioned, this is an easy topic. If you have any question, ask it. We don't have any numerical questions in the in the lecture notes, but we have numerical questions in the tutorial. And also there are Frankel defect and Shoki defect. So there are two names given. When you have a cation vacancy, cation interstitial pair, then you say it a Frankel defect. So you can see a Frankel defect here. So you can see a cation vacancy here and a cation interstitial. So this cation has moved to a different place. So here you have an interstitial defect, and here in this space you have a vacancy defect. So when you have both together, we call it Frankel defect. And Shoki defect is a pair of set of cation and anion vacancy. So you can see here a cation is missing, and here an anion is, sorry, a cation is missing here and an anion is missing here. So anion is a big one. So this one is the anion and this one is the cation. So both together missed. So we call it Shoki defects. So you need to know when you have these pictures and when we ask you to name them, for example, which one is what. So you should know which one is what. Or else in this one, when we given all these vacancies and all these defects, you should be able to identify which one is what. Okay, so to find the number of defects here in ceramics, the only difference you have is you have here 2, because it's all together like, 2, here you have 2 defects together. So when you have 2 defects together, you have Franklin effect, this number of Franklin effects as a, you need to divide by 2. So in the exponent, so it is twice, it will become twice when you get to the exponent to the power. Are we good? Any questions so far? So these equations, you don't have to remember, these will be given to you, but you need to know how to substitute the values and find them, and we are going to do it in the tutorial. Any question? So far we have discussed about the defects. So we discussed about the point defects in metals and also point defects in ceramics. Now we are going to discuss about the impurities. So when we have some impurity in the metal, what will happen? So impurities are not a disadvantage all the time. If we purposely adding impurities to metals to improve properties. For example, we add carbon to iron to make it steel. So when we have carbon, it's stronger. So we use it. We use, even though we call it an impurity, it's an advantage for us. So you can see here carbons in iron. So carbon atoms are very small. So you can see carbon atoms are staying in between the iron atoms. So it is interstitial impurity. But you may heard of alloys as well. Alloys are made up of, like, carbon is tiny, but when you have both metals in the same atomic radius, we can have substitutional atoms. That means you are substituting. So they are not staying in the interstitial sites. They are taking the space of another atom. So you can see here copper in nickel. So it's an alloy. So that we call a substitutional solid impurity. Also, we can have a solid solution. For example, we have copper and nickel together in 2 different compositions, but we can have both in together. So you can see this one is an impurity, but it is not just one atom. It is a solution of 2 things. This one, again, the big area here, also a solution, but you can see there is a difference between these 2. So you can see here, this is arrangement, and also the percentage of the 2 components are different. So that kind of a solution defects, we also call it as a solid solution B in A, plus particles of new secondary phase. So it's making a new secondary phase, this one. So this new secondary phase can be different in the composition, or else it is different in the structure, or either both together. So do you understand these differences? Interstitial, substitutional impurities, and this phase Any question? Any question?
What is meant by second phase particle?
It can be like, it's the same thing, A and B. So you can see this, without this one, you have A and B together. Am I right? It is a solution. So when you have two things together, we call it a solution. So this one again, a solution, substitutional and institutional. So for example, let's take a substitutional solution. So in the substitutional solution, you can have another substitutional solution made up of A and B, but the composition of A and B may be different. In the first one, maybe you have A 30% and B 70%. In this part here, you may have 50-50, 50A and 50B. So they are not the same. This whole area is like, that phase is different. Make sense?
Yes, thank you.
Do we have to know what these are?
What's that?
Do we have to know what these are?
What do we mean?
Do we have to know what these things are?
You need to know, like, as I have told you before, when these pictures are given, you should be able to say this is an interstitial impurity. This is a substitutional impurity. So this is substituting. It's not staying, these copper atoms are not staying in the interstitial site. So they have the same radius. So they are substitutional. And when you have carbon in iron, carbon atoms are small and they squeeze inside in between the interstitial site. So that is an interstitial solution. So if these names are not given, you will be able to identify which one is what.
Thank you, Miss.
Okay. Okay, so and also this is not just the composition, the structure as well. So you can see here the way this arrangement A and B are staying like this here, but in this one they are staying in a random way. So it can be either the composition or either the differences in the structure or maybe both.
So, Miss, there's two types of solid solutions, substitutional and interstitial.
Yes. So yes.
And B would be second phase particle, or
A and B can be anything. Okay, so here we have substitutional. So in this example, we have substitutional, both atoms are in the same size.
okay. Yeah, I'm not quite understanding, but I'll go over it anyway. Thank you.
What you want to get clarified?
I'll come back. I'll come back later.
Okay, we'll do this and we can come back. Okay, this is a short, small lecture anyway. Okay. So now we should know to have this substitutional impurity, substitutional solid solution. All the metals can't be in the substitutional. They can't, like, any metal can't be in with another metal as an alloy, as a substitutional, because there are few things to satisfy, to stay together. The things are atomic radius. So both the atoms, copper and nickel, for example, here, copper and nickel, if we consider, they can stay together and they are making an alloy. They have the similar diameter, similar radius. So you can see the radius of these two. So they are very close. If you consider the change in the radius, it is 0.003. If you take it as a percentage divided by the radius of one of these, and times by 100, you get only 2.3% difference in the radius. So if the difference in the radius is less than 15%, these two elements can be together as a substitutional solution. Okay, and it's just one requirement. There are few other requirements need to be satisfied to stay two metals together as substitutional solution. So the crystal structure should be the same. What do we mean by the crystal structure? We discussed this last week. What do we mean by not last week, the week before, last week tutorial? What do we mean by the crystal structure? What do we mean by the crystal structure?
PC, BCC.
Yes, so BCC, FCC, HCP, those ones. So both the elements should have the same crystal structure. So these two are both FCC, FCC. So that also satisfying. So radius requirement is satisfied. Crystal structure requirements also need to be satisfied. So they both should be in the same crystal structure. And the electronegativity, similar. Electronegativities should also be very close to each other. So you can see electronegativity is 1.9 and 1.8. So they are close as well. Valence. Valence is the how many electrons at the outermost shell. Other factors being equal, when everything is equal, the metal will have a greater tendency to dissolve a metal of higher valence than in a lower valence. So copper would like to dissolve in nickel than dissolving in another one with one positive one valence. So do you understand what I mean? So an element would like to dissolve in, if these all three are satisfied, they would like to dissolve in a metal with a higher valence than with a less valence. Valence means the number of electrons at the outermost shell. Are we good? Are we good? Any question? Okay, we have questions in the tutorial. Okay, so you can try them before the tutorial class if you are interested. Next week, we are going to do that. Okay, now let's see the impurities. So these are the impurities in metals. So we will discuss about alloys more when we do the phase diagram. So alloys are very important. We can have two or more metals together with an improved properties. So we will discuss. And also carbon in iron is very important for us because steel, that makes steel. So you have heard of many applications of steel than iron. Iron is very, it can corrode easily, but steel is stronger. We can have case hardening with more carbon together, mild steel, stainless steel. So we have different kind of steel with the different composition of carbon added to that. So this is, even though we call it an impurity, we are purposely adding these substitutional or else interstitial atoms to a metal to improve properties. So we'll come back to this when we do phase diagrams later on in one of the weeks. So now let's see the impurities in ceramics. So ceramics is always two things together. We have a cation and anion, for example, sodium and chlorine. So sodium is a cation, so we have a smaller radius, and chlorine is an anion and it has a larger radius. So we can have substitutional cation impurity. So cation impurity is, you can see, we have a calcium cation as an impurity. In the sodium chloride, we have a calcium as an impurity. When we have an impurity in ceramics, there is an important thing that we need to remember. So charge should be balanced. So negatives and the positives should be balanced. So it should not have a net charge. For example, sodium and chlorine, 1 sodium to 1 chlorine. So if you count the number of green and the blues, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, and you have 8 blue and 8 green atoms. So this is charge is balanced. But if there is an impurity of calcium 2 plus, to make the charge balance, it should be replaced to 2 sodium atoms. So 2 sodium atoms should be taken off, and this one can stay here as an impurity. So you can see there is, when you have this one, calcium 2 plus cation as a impurity, there is a cation vacancy as well, because 2 went out and just 1 came in. So you have a vacancy here as well. So this is creating an impurity, and also it is creating the defect of a vacancy as well. Does that make sense? Is it clear? It is the same with the anions. You can see we can have oxygen as a impurity, oxide or O2 minus. If we have as this is valence is O2 minus, to have this one here, we need to take off chlorine, 2 chloride ions. So when you take 2 chloride ions, there is a vacancy created that is a anion vacancy with an impurity. So you need to mention both of this. If you just say with the oxide impurity, it's not complete. So it is having an impurity and also it has created the anion vacancy, because just to make the charge balance. So you can't have like, both together, both elements together, or all 3 elements together, the net charge should be 0. Is it clear? Any question? So we are finished with the point defect. So with all this, do you have any question? Are you guys there?
Must we know like
No questions.
must we know all bonds like either than NaCl or other things? Must we know like what they are in terms of neutrality?
You don't need to know.
Must we be able to point out?
When the periodic table is given to you, if
Yeah.
these kind of questions are there, we will give you the periodic table. If you have the periodic table, you know how to find the number of electrons at the outermost shell. Am I right?
Yes.
Yes. So in that case, you will be fine. But like, mostly the thing is, as I have mentioned, you need to understand these terms. So what do we mean by substitutional cation impurity? So you need to know what kind of, what is it, isn't it? So what do we mean by substitutional anion impurity, and why it is creating a vacancy as well if we have 2 plus. If you have like, just 1 negative, this vacancy is not created. This vacancy is created because you have 2 here and only chlorine has, so it should replace 2 chloride ions to come the oxygen to come here. But if you have something like A, for example, 1 negative, only it doesn't create an ion vacancy. It is just an impurity. Do you understand what I mean or not?
Correct.
Okay, that's good. Okay, so now we are done with the point defects. We are going to move to linear defects. So dislocations. We will do in one practical, we do the tensile test, tensile elongation. When you apply a tensile force to something, you can see this change in the shape. So that it's something we can't see it with eye. You only see the change in the area like this. So linear defect is 1D defect around which atoms are misaligned. So you can see atoms are misaligned in this one because of the tensile elongation. Slip between crystal planes result when dislocation move, produce permanent deformation. So that will, even though when you take the force out, it won't come back to the original shape. So it will stay there. So, so this is a schematic of zinc. Hexagonal closed pack. Zinc has a hexagonal closed pack. So before deformation, it's like this. And after tensile application of the tensile force, it will be like this because the crystal planes, so there is a slip between the crystal planes and it is a permanent defect. And we can have edge dislocation. So we can see this one here is additionally has been there. So extra half plane of atoms. This is a plane, okay? So this is 2-dimensional. Sorry, this is whole plane of this one. So you don't see that. So extra half plane of atoms insert in the crystal structure. So it is you can see what has happened. So this is the no, this part is okay. So you can see a dislocation here. The amount of this location, the B perpendicular to dislocation, so that we call a Berg vector. So Berg's vector, B magnitude and direction of lattice dislocation. So you can see that here. So that we call an edge dislocation. When this picture is given and when we ask you to identify what kind of defect this is, you should be able to identify it as a edge dislocation. Also, we can have, so here you can see dislocation motion requires the successive bumping of the half plane of the atoms from left to right here. So you can see it's gone left to right. This part is okay. This part has gone from left to right. Bonds across this slipping planes are broken. So here, this is your slipping plane. The bonds between here, the bonds are broken and remade its succession. And also we can have screw dislocation. So you can see it is like, screwing. Spiral path result from shear deformation. So it is shear, it's like a screwing rotational one. So you can see something like this. So it's not just slipping. It is just like a rotation. If it is slipped, then you see the same distance from everywhere. So, but this is just a rotation kind of a thing happened here. We also can have both together, edge defect and the screw defect together. So you can see here we have a screw defect and here we have an edge defect. So both, because of these two, somewhere here we can have mixed defects. So that here, because of the two effects together, so there can be places where we have the mixed defect. So this is a software. You will be able to create this, and you can rotate and find out how it look like. These pictures, they are not like, you can't visualize easily, but when you do the practicals, you will be able to see these ones, rotate and see what do we mean by these different types of like defects. Okay, so this is just a software where you can see this rotating and see the defect from different angles. Okay, another one is grain boundary defect. So you can see these are the grain boundaries. So grain boundary is the interface between two grains or crystalline in a polycrystalline material. So grain boundaries happen because, like, if there is two different phases, you can see its alignment is changing in two grain sites. So this the space in between the two grain sites we call the grain boundary. So regions between crystals we call the grain boundaries. Transition from lattice of the region to that of the other is like the grain boundary defects. So slightly disordered, we can't say where it is just randomly staying. Low density in grain boundaries, high mobility, high diffusivity, high chemical reactivity. So grain boundaries are weak because if we have a continuous this staying in atoms in the same way, it is stronger. But in case if you have two different, this is happening when you heat up and cooling down a metal, depending on the cooling rate of different sites, the arrangements will be different. So we can have this kind of orientation in one part and this kind of orientation in another part. So these areas where you have a boundary, so this one we call the grain boundaries. They are weak places. So it is again a defect because it's breaking the continuous way of arranging atoms. Does that make sense? Okay, and also we can have interfacial defects, like, we call that the planar defects. So here, one example is twin boundaries. So if you also can and see this in 3D in YouTube. You can see it in different angles if you want to. I got this from Google, so I hope you can see the difference here. So here, a twin boundary is a specific type of plane defect in crystals where two regions of the crystal shares a common lattice plane. So you can see there's a common lattice plane here, resulting in a mirror image relationship. So they have two, like, they are in opposite sides between the two regions. So you can see the two regions have opposite properties. So that kind of a case we call the twin boundary. And stacking faults, again, another defect. You can see for FCC here, and in FCC, so you can see this is with no defects. So you can see how they stay. So you can see A, B, C, and again A, B, C. So you can see this is staying like this, A, B, C, like this. Arrangement, see, the arrangements are like that. So there is no defect in this. But if you go to the B, you can see ABC is staying like this. In the next one, so you don't see that same structure, isn't it? So here again, you can see ABC, but here you can see something different. So that kind of a change in the arrangement, we call that stacking. It is the way that it is packing. So we call the stacking fault. Does that make sense? Are we good? Okay, so that's what we have for today's class. So we discuss about what the point defects, line defects, insufficient defects, all that. We have some equations where we have to use in the tutorial class to do some numerical questions. So calculate the equilibrium number of vacancies. It depends on the temperature. You can remember the temperature was in the equation. So we are doing this in the tutorial. Describe describe and identify edge, screw, mix, dislocation. So I told you, you should be able to identify when the pictures are given to you, you should be able to identify which one is what. And also to identify, you should have the knowledge what that means. Edge defect means what? Screw defect means what? Shoki defects means what? Frankel defect is what? So you need to know which one is what to identify them. Okay, so these ones are important for your quiz 1, okay? So, do you guys have any questions? So it's a short lecture, but we have time. If you have anything, we can discuss.
Yeah, miss, the substitutional defects. I mean, the substitutional impurities.
Yes. Substitutional.
Miss, can you upload this lecture straight after, please? Because
I will do.
I usually get some time before you upload it, and I want to study it because I have to go over it again.
Yeah, I will do that. It will take about 10 minutes for me to get the link, and I will straight away do that.
No worries. Miss, as well, do you have any sample paper? Because our quiz is in 2 weeks.
I told you I will upload some, right? Yeah, I will upload it. Yeah, tomorrow morning I will do that. Okay.
Please, miss. Yeah. Let me know.
Yes,
Let us know or something. Will you email us?
No, I will put it in the views under the assessments. Let me check.
Will you send us announcement on the email?
Yeah, I will make an announcement as well, and I attach it in the announcement. Yeah, I will put it in the views so that everyone can see. I don't need your student number. I think in Zoom, I can find out. If you have your right name, I will be able to mark your attendance. Okay, it's recorded in the Zoom. When you joined, when you are leaving, everything is recorded in view. So yeah, I have all that. Okay, so let's do this one. So substitutional solid solution. Solution means like, you know, when you have sugar, liquid solution, for example, if you add sugar to water, it is making a sugar solution, sugar in water. Solution means many things together. Okay, when you have pure elements, it is not a solution, it is just a pure element. But when you look at metals, we have metals as a solution, solid solution. We can have them in two ways. One is as a substitutional solution where copper and nickel together making an alloy. We call it substitutional because, for example, if you have nickel only, that will stay like this. Substitutional means you are adding some copper to that. So it is not squeezing inside and staying in the interstitial sites. Interstitial sites are these ones. So these are the interstitial sites. So this nickel, copper cannot be stay in the interstitial sites because copper has the same diameter as the nickel. So what it does is it is replacing this, substitute this. Instead of having a nickel, this one will put the nickel out and the copper will be there. So likewise, we call when it is substitutional. You don't have the nickel there, you have the other type copper here. So this kind of a thing we call the substitutional. But if you consider iron and carbon together, iron will stay like this. And carbon atoms are very small. They don't have to replace iron to stay inside this iron. So they will squeeze inside this interstitial sites and they are again a solution. So I hope you can understand the differences between these two. This we call the substitutional because it is substituting, replacing. This we call the interstitial because it is just staying in the interstitial sites. Does that make sense, Mohammed?
Yeah, I sort of like got it. Yeah. Maybe I'm fine of remembering it or something, like remembering how it will go.
But you understand how
Yeah,
the
I
difference,
understand
right?
they're
Yeah.
substitutional and the other is
Interstitial.
interstitial.
Yes.
Yeah, got that.
So are you okay with this solid solutions again, like, you know, staying a solid? Is this clear to you or not?
Um, the first part or the second
Oh,
part?
this one here, solid solution.
Yeah, I didn't get that part either.
Okay, so so now let's see that you have this. You have a substitutional one here. So substitutional means what you have here and there, you have like, you know, the copper and nickel like this. Okay, now again, you have something like this. For example, you have an arranged structure. So these both have nickel and copper. Am I right? Both have nickel and copper. But if you look at these two, they are two different structures. Here you can see alternatively staying nickel and copper as like this. But here it is randomly staying. In the top one, you can see randomly staying. In the second one, you can see arranged that they stay like in a pattern, isn't it? Am I right?
Yes, miss.
So here, when you have this, and also the composition also different. Here maybe you have about maybe 40% of nickel. Here maybe you have 30% of nickel. The composition and also the structure are different. But when you put these two together, this one, if it goes here, this is here at the beginning also there are impurities, but now you have more impurities as a solution. So this one is going to stay in this one as a phase, a secondary phase. Make sense?
Yeah, sort of got it, miss.
Okay. Yeah, so these ones are hard to visualize, but like, you know, when we do the practical with the software, you may be able to see this. I think there should be some stored ones. We'll check, okay? Then you can visualize, you can see it in the computer screen, three-dimensional. Okay, what else?